So, just going to go over a little plan for today. This is my first Linkerd-proxy stream, and so we wanted to do just sort of a little tour for Linkerd users and contributors to familiarize all of you all with the proxy code base. And I thought that it might be fun to eventually start doing like live coding and stuff as well. So, maybe in the future we'll get to that. So our little agenda for today is just going to be, let's see. So I just want to see, in general, the audience that we have here today to see, like, what people's level of background knowledge and, like, if you're familiar with Rust, already using Linkerd, or if all of this stuff is new. So in a little bit, I'll just ask, like, the chat to try to get... okay, great, Manish. Thank you for helping out with sort of establishing that. So... it would just be great to know, like, how many of you right now are Linkerd users? Have you tried it out at all or looked at it? Are you using Linkerd in prod? And how many of you are familiar with Rust? Have you seen Rust code before? Or never seen it in your life? Because, that'll kind of inform, like, the direction that we're going to take this and how long we focus on different things. So I'm just going to sort of give people a little bit to start answering some of those questions in the chat. Just let me know, and then I will keep going over our sort of agenda. So then we're going to do sort of a little overview of the proxy, what it does, how it's structured, and depending on how many of you are already familiar with Linkerd, how much time we'll spend on that might vary a little bit. And then we'll look at basic Rust, sort of overview of syntax and how to read it, so that as we start to look at the actual code base, everyone can follow along, even if you're not a Rustation, you haven't really read Rust code before. And again, if we have a lot of folks in the stream here who are very familiar with Rust, we can abbreviate that. And if more of you have never looked at Rust code, then we'll spend a little more time breaking that down. And then we'll look at some of the basic proxy building blocks. And how we do asynchronous programming in Rust and what that might mean. And then I'm not sure how much time we're going to spend on all of this, so by the end I figure there is probably time for some Q&A. Hi, Jack. So I'm just streaming a little intro to the Linkerd-proxy code base, and we're just now going over sort of today's little agenda. And, over the next few streams, I'd like to sort of do a tour of the project and start to dive pretty deep into some parts of the code. And then once we've sort of done a full tour and explored the whole code base, I would love to try my hand at maybe some live coding in mostly Linkerd or for Tokyo or other Rust open source projects. So... let's see, are people still joining, or is this the crowd for now? Okay, so we have some Rust users, some Linkerd users, and then we have, it looks like, a bunch of folks in chat. So, of course, if we move too fast for anyone, please let us know, and we can slow down and sort of break things down more and go into more detail. So first, to get started, we're just going to look at the Linkerd-proxy, and I have, I want to be on the main branch. Oh, I have a dirty working tree. Okay, let's please disregard this. Let me just get this cleaned up so that I should have done this of course, before we started the stream, but I didn't, think of that in advance. Hi. So I'm just going to stash my Git history, and we're going to check out the main branch. And so what is Linkerd? Let's take a look at the README. So Linkerd is a service mesh for Kubernetes. And if you're not familiar with Kubernetes, Kubernetes is a scheduler for containerized applications and a runtime environment that handles things like networking at a certain level. And so Kubernetes is basically a system where, yeah, sure, let's make the font a little bigger. Oh, that's the opposite of bigger. So is this good? Can everyone see this? Does this look good? Hi, Camille. Is this a good font size? Okay, so we're just looking to README here. And Linkerd is a service mesh for Kubernetes. So what that means is that it is an infrastructure layer that consists of proxies that are deployed side by side with application containers, and a control plane that manages the proxies. And so what happens is that Linkerd is injected into an application container, and when that happens, we do some IP tables magic, and basically we configure IP tables so that the kernel in the container sends all of the TCP traffic that is coming into and out of the application container through the Linkerd-proxy first. And so what we do is, it's what we call a transparent proxy. And so that means that the application doesn't have to be aware of the proxy in order to communicate through the proxy. Instead, we sort of transparently intercept traffic to and from the application, and we can do things while it's on the wire, and then we forward that traffic to its destination, and then a proxy on the receiving end can then communicate with the application on behalf of the proxy that sent the message. And in doing that, we can do a lot of things like improving reliability for the messages in flight, intelligent layer 4 load balancing for non-HTTP traffic, automatic latency-aware layer 7 load balancing for HTTP and gRPC traffic. And we can do a lot of observability features as well, like we can record request level metrics, and we can do distributed tracing. We can provide a diagnostic tap feature where we can look at live traffic flowing to and from containers in the mesh. So the proxy is written in Rust. It uses asynchronous I/O and is implemented using Tokyo and Tower, which are sort of major Rust libraries that we'll take a look at. And so let's talk a little bit about the proxy organization. So we're going to take a look here. Why don't we start just looking at the entire proxy repo. Oh god. So as you can see over here, we have a Linkerd proxy directory, and this is sort of the main application binary, and we just have a main here. And this is our main method, our main function, and as you can see, it's really pretty short. So this basically just reads configuration from the environment, and then it sets up the Tokyo runtime that we run the proxy on, and then it just calls app.spawn and waits for the proxy to shut down. So the main is really very simple. And then all of the meat here is in sort of a big pile of crates. And for new Rustations, crates are sort of the Rust unit of granularity for packages. So a Rust package is called a crate. Libraries are distributed as crates and so on. And so over here, all of these directories that are in the Linkerd directory are all sort of subcrates that have like one proxy component in them, and the proxy components are written in a very modular way. So then when we actually build the proxy, we just sort of plug these modular components together, and we get a proxy that does everything that Linkerd does. And so basic Rust syntax, we'll start here in the main.rs file. Rust has a module system, so you import names like types and functions from modules with use statements like what we see here. So we're just using the Linkerd2 app crate, and we're importing the function or the module trace in that crate, and we're importing a type called config. Now, functions and modules are going to have names that begin with lowercase letters. Types are going to have names that begin with uppercase letters. So, you know, and that's just by convention. But that'll let you see whether, when we see some name, whether it's a type or it's a function or a module. Furthermore, we also have Rust macros, and they end in bangs. So here, like ePrintLine is actually a macro, and you can see because it has the bang, and my VS Code is highlighting in a different color because it's a macro. So then we have the sort of : operator, which is the namespace resolution operator a la C++. So when you have a module and that module has some name that you want to import in it, you say use the module : the imported name, and that's how you sort of resolve that namespace. And also types can have associated functions. So here config : try from env is calling a function that's defined on the config type. And if we just click through and see that, see here, here's a function definition. They begin with fn is the keyword to define a function. There's the name of the function. I'm just trying to hover over stuff, and I guess VS Code wants to show me like the documentation for all of those types. I should turn that off. And then you have a list of parameters in parentheses. This function doesn't take any parameters. You have an arrow, and then you have a return type. And here the return type is a result, which is a generic type, and it's parameterized over a self and an error. And result is sort of the basic unit of Rust error handling. A result is, let's click on it. We can just go take a look in the Rust standard library. So here's result, and a result is an enum, and an enum is an algebraic data type. So it's a sum type, where we define the enum as having two variants, and it has a variant called OK, which is a value of type T, and it has a variant of type air, which is a value of type E. So a result is one of two types. It's an either type, but the naming of the result type is sort of specific to it's either a success or an error. So if you've written Scala, this type in Scala is called try. If you've written any Haskell, this type is called either, and it's just conventional that one arm of the either is the success and the other side of the either is the error. And if you have not written Scala or Haskell and you are more familiar with imperative object-oriented languages, this probably looks pretty weird to you. So also I realize now, because we're looking at the standard library source code, there are all of these attributes, and the attributes are beginning with a hash and then square brackets, and then there's an attribute. And these are like annotations or compiler pragmas that are not part of the actual Rust code, but they're telling the compiler or some additional tool to do something, like must use is saying that if you don't consume this type, the compiler should make a warning in code that uses it. And then these stability attributes are for how the standard library is versioned, and they are really just ignorable, and we can ignore them. So, this is not as clean as we would like because it's in the standard library. But sort of an example of a Rust type. And as I was saying, if you are used to a language like C++ or Java, you might handle errors by throwing exceptions. In Rust, all errors are return values. So instead of saying I'm going to return, an integer or something, and if something goes wrong in the process of returning that integer, I'm going to throw an exception. And then the exception is caught in the calling scope. Instead, in Rust, you would write, again, like this function that we were looking at before we got here, which was try from n. So instead of saying I either return a self, which is this config type here, or I throw an exception, instead you say I'm returning a type which is either a self or an error. And so that's sort of the fundamental principle of Rust, error handling. So let's pop up the stack a little bit and go back to the proxy's main function. So this is a free function. This is not a function on a type. It's not a method. It's just fn main. And this is where we build the proxy. So here's an example of that error handling. We have this call config try from n, which we just looked at, and that returns either a config or an env error. And then we have this match keyword. And so match introduces pattern matching. And so what we're doing in this pattern match is we have these two variants of the result type, right? It can either be OK, or it can be an error. And if it's OK, there's a config. And so if it's OK, we extract that config and we assign it to this config binding. And if it's an error, then we handle the error here. So instead of having a sort of first-class notion of exceptions, we just sort of pass around these data types that we then match on their values, or we can do other things. There are combinators, but sort of the primary principle. And then here we handle the error by we print invalid configuration, and then we format the error, and then we exit with an error code. So that's sort of the beginning of our introduction to basic Rust syntax, which was not my plan. I wanted to look at the organization of the project first, but I got a little carried away. So then you see function calls have parentheses after them. Sometimes they have parameters. And I am using a Visual Studio Code extension that shows the names of the parameters in line. That's not actually part of the code here where it says future. That's just being added by the Rust Analyzer VS Code extension. Maybe I should turn that off for future streams, but just wanted to clear that up. So we have this proxy. We have this sort of main, and this is the entry point to the actual production proxy application. And then we have this sort of big pile of stuff. And you look through here, you see some pretty generic sounding names for different modules of the proxy's behavior. Sorry, like we have adder, admit, buffer, cache, concurrency limit, conditional, DNS, and so on. And these are each their own little Rust library that the final proxy project actually depends on. And we do this mostly so that the changes to different parts of the proxy codebase are self-contained and have sort of well-defined interfaces between each other. So it's sort of like we are, instead of writing just the proxy executable, we are writing a big pile of libraries that you use to write a proxy and then just plugging them all together. And I think this has been really successful because it makes sort of the scope of changes to functionality very easy to sort of manage and know where to go. And also, it makes the Rust build a little faster because unchanged crates can be cached. So that's also kind of nice. And these little sub-libraries are still more Linkerd specific than like a general purpose library. They are libraries that were written for the purpose of putting them together to build a Linkerd proxy, and so they sort of depend on Linkerd specific assumptions and interfaces. But below that layer, there are also libraries that we depend on from the Rust community, some of which Linkerd's maintainers have contributed a great deal to. And the sort of core interface, the sort of core abstraction that we use as the boundary layer between all of these sort of sub-libraries in the proxy is from a Rust community crate, and we'll take a look at that in a little bit. So our agenda, proxy overview. How's it shaped? So we think a Linkerd proxy is a little bit different from like a general purpose reverse proxy. It's also a little bit different from the Linkerd 1 proxies that I know Aman has used and maybe some others in the stream. And so for those of you who are already Linkerd users, you probably already know this, but these proxies are intended specifically to be deployed as sidecars. And in sidecar is like a piece of Kubernetes terminology. What it means is that it's a container that's scheduled side by side with the application container. So when you spin up an application, you want to deploy a bunch of application services. You have some service that you want a bunch of replicas of. You say, I want to deploy this container, and I want like 100 replicas of this container. What happens is the sidecar, like every time that container is scheduled on a host or on a worker node, it has a sidecar container that's scheduled alongside of it. So every application instance has its own separate proxy. And because of that, the proxy is shaped in a particular way. It's not sort of a centralized routing proxy that sits on one node and then all of the other nodes talk to it and then it forwards traffic out into the rest of the cluster. It's not a sort of host agent, or in Kubernetes the name for this is a daemon set, where there's like one proxy deployed per host and all of the application containers in that host talk to that proxy. Instead, the proxy is deployed side by side next to every single application container. And because of that, it's shaped in a particular way. We can talk about all traffic that flows through a Linkerd proxy as either being inbound traffic or outbound traffic. And inbound traffic is traffic that's coming from the outside world to this container, right? So somebody else is sending some TCP traffic to our IP address, and we have, when we injected the Linkerd proxy into this application, we set up the IP tables rules so that all incoming traffic to our IP address is forwarded to a particular listening port on the proxy. And so then we take this inbound traffic, we look at it, maybe if it is a TLS connection and it's encrypted, and it has an SNI in the TLS handshake, a server name identification that is our SNI name. If we know that it's for us, then we transparently decrypt it and handle it by sending the plaintext traffic to the application container. If it is been upgraded to HTTP2 for performance improvements on the wire, then we downgrade it back to HTTP1 before sending it to the application container, and so on. And then we record metrics about the incoming traffic, and so on. And then we forward it on localhost to the application, and the application can just listen on localhost, and it receives all of the traffic that was intercepted by the proxy. Then we have outbound traffic, which is like when the application container wants to talk to anybody else. So if you, you're sitting there, you want to call some other microservice, or you want to hit an external API or something, you open an outbound TCP connection, and again, the IP tables rules are configured so that when you try to open that connection, the kernel intercepts it and opens it to a different listening port on the proxy, and that's our outbound listener. And the outbound listener, does similar things, except it's a little bit more complicated because when you are talking to the outside world, Linkerd can do load balancing and routing. So we do service discovery, we try to figure out where that connection is going, and we try to balance over the available endpoints for that connection, and then we forward it. And if we know that the recipient of that connection is also a Linkerd-proxy, which is when we would say this connection is in the mesh, there are a lot of sort of extra magical things that we can do. We can make it faster, even though we're adding more steps, by using more intelligent load balancing, by upgrading HTTP1 to HTTP2, so that the messages on the wire can be multiplexed more efficiently on one connection. And we can do sort of a big Linkerd feature, automatic mutual TLS. So the application can believe that it's just talking to another application container in plain text. But the messages on the wire are encrypted, and we're performing TLS with client auth. And so you can drop Linkerd into a totally plain text application that maybe has some ingress proxy that when requests come into the cluster from the outside world, like from your users, you terminate TLS there, and then all of the communication between the various backend services in the cluster is totally unencrypted and totally plain text, and you are relying on that sort of perimeter model of security. But that's not really all that good, especially in a sort of cloud-native world where these applications are running on hardware that you don't own, and they might be co-located with other people's code that you don't know anything about, and you're sort of living in this world where you can't really rely on that perimeter of, we have the one big ingress proxy, and it terminates all TLS for, mywebsite.com. Oh, this is a great question from another Walter. How would this compare to kube-proxy, or ELBs defined as load balancer services? That's a great question. So kube-proxy, so the big difference is that kube-proxy and ELBs are both transport layer proxies. So they operate at the level of TCP connections, right? So kube-proxy is actually not so much a real proxy as a big pile of IP tables rules in many Kubernetes implementations. So it just configures these connections go to these places, and that's very nice because you don't have some other program that's in the data path, but it's operating at the level of TCP traffic. The same with your ELBs, your Amazon Elastic Load Balancers, is they're also TCP level load balancers. And so that means they don't know about the semantics of higher level application protocols, layer 7 protocols like HTTP, like gRPC or gRPC over HTTP2 or WebSockets. They don't know how to load balance those higher level protocols. They only know how to load balance at the level of TCP connections. And at the level of TCP connections, the kind of load balancing that you can do is not very smart. And what I mean by not very smart is, okay, so you have these TCP connections. You don't really have a concept of latency at the level of TCP, right? You have these opaque byte streams, and that's all a TCP connection is when you are in ELB. It is a bunch of bytes that are going in one direction, a bunch of bytes that are going in another direction. What do those bytes mean? We don't know. They might be encrypted. It might be TLS, and we can't decrypt that TLS traffic because we don't have the key, we don't know what it is, but also we don't care because fundamentally we are not operating at the higher level of the TLS protocol. Some of those bytes that are going on that connection might be HTTP requests. You know, they might be the ASCII bytes get/HTTP 1.1. But we don't know because we're just treating them as opaque bytes. And so because of that, we don't know this is a request. We don't know this is an HTTP response. We don't know what the domain name that the request was sent to is. We don't know any of that stuff because we're operating at the connection level. And if you want to have latency-aware load balancing, which is what Linkerd does, we are actually looking at the latency per request. So when we see a request coming in, we look at, all right, how long does it take until we get the first byte of the response to this request? How long does it take until the response stream finishes? And we can use that to make smarter load balancing decisions. But we can only do that when we're actually aware of the higher level protocol semantics, right? We have to speak HTTP because we have to know what a request is. We can't talk about request latency unless we know which bytes are a request. And in order to operate at that level, you have to be able to actually speak that protocol. So your ELBs are just doing what's called round-robin load balancing. So you know all of the endpoints that are in that load balancer service. You have a big list of IP addresses. Every time a new connection comes in, you pick the next one. You know, you have some index that you increment on every connection. You index that big list of all of the IP addresses that comprise that service, and you just keep going. And next connection, you increment it, send it to the next one. So you're doing this sort of round robining, and that's good because it is spreading out the load. But what it's not doing is responding to the performance of the individual replicas. With latency-aware load balancing, we make the load balancing decisions by picking the replica with lower load when we send the request. So we do this because we've been sort of tracking how long it took for a response to each request sent to that replica to come back. And by sort of tracking those load averages over time, we can send more traffic to the hosts that are able to handle it faster. And the very cool thing about this that I just think is especially magical is, you know, a lot of people talk about like, oh, we want like some geographically aware routing, you know, where let's say you have, you know, a bunch of servers in a data center and you have a data center that is, you know, in Fremont, right, about an hour from my house, and then you have another data center that's somewhere in Europe, and you have a data center in mainland China, and you have a data center in US East 1. You know, you have these sort of data centers all over the world, and maybe these are not your data centers. Maybe they belong to AWS or something. And so when you're writing your application that's deployed to the public cloud that's running on AWS, you don't necessarily know like which exact AWS data center am I in. I'm in this availability zone or that availability zone, but your application isn't super aware of where I am. And then within that data center, like, you know, an AWS data center is a huge building, right? Does anyone know how many square feet an AWS data center is? I know we have at least one Amazon employee in the chat. So, so you know, that's a big building. And then you have these racks, and in each rack there's a bunch of servers. And then you have a top of rack switch or something. And so you have an Ethernet cable that's plugged out of your back into one of the Ethernet jacks on that top of rack switch, right? And then there is a really fat cable that comes out of that top of rack switch, maybe to an end of row switch, and then from the end of row switch to some switching fabric, right? So let's say like you have this Kubernetes application, and Kubernetes is not really scheduling at the level of those physical machines. If you're running in the cloud, you're scheduling onto VMs that your cloud host is giving you. You know, and if you're using a cloud provider's managed Kubernetes service, you're just scheduling onto some Kubernetes workers that they're running for you, and you don't really know what machine they're on. And so it would take a lot of effort and a lot of work to get all of this information back into the system about like is this particular endpoint that I might talk to, this one instance of this service, is that running on maybe the same host, right? It could be in a different VM that's running on the same rack server. Okay, it could be on a host that's on the same rack, so it could be like right next door, and if I talk to it, it only goes to that top of rack switch and then back down. It could be on a different corridor in the same data center, so somewhere in the same building, different row. So it goes top of rack switch, end of row switch, top of rack switch, down to the server, right? Or maybe it's in the same availability zone, but not in the same data center. So it's just somewhere in like US East 1, and maybe there's another data center in US East 1, maybe it's the same campus, or maybe it's somewhere totally different, and so I go, you know, out of my server, top of rack switch, end of row switch, maybe on some fiber that's run between two buildings, end of row switch, top of rack switch, down to that server. Okay, maybe it's in a different availability zone. Maybe it goes end of row switch, top of rack switch, so on, and goes over as undersea trunk line to China, and then, you know, that's obviously much slower. A lot of this is over fiber. Signals on fiber propagate at the speed of light. Speed of light's not that fast. There's a noticeable lag. There's like some actual latency just from sending that traffic on the wire to you know, the next row in the data center. There's even more noticeable latency from sending that data on the wire, you know, under the subsea trunk line to another continent. And if you don't have that geographical information sort of encoded in your service discovery system, you're not picking the closest replicas preferentially, because you don't know what close means. But the downside to that is that you have to expose all of that data, and that's like a big pile of work. And it's an even bigger pile of work when you're running on hardware you don't own, on VMs that you don't own, in the public cloud. So if you load balance based on latency, this is sort of an emergent property that you end up routing traffic to closer hosts just automatically. They have lower latency, so you pick them. You pick them preferentially, so you get this sort of nice, like, routing is faster because all of the traffic is, you know, maybe on the same host, same rack, you know, preferentially picking some geographic locality, but it's not encoded into the system. It's just an emergent property of looking at latency. And looking at latency also means that you pick the least loaded replicas. If somebody is on, you know, the same, you have some server and you're talking to that particular server and it is running an application instance that's getting a whole lot of traffic, its response time is going to go down, so that latency is going to be higher, and you will just sort of gradually start shifting traffic to a different replica. And this is really magical, right? Because if you are load balancing based on just these latency measurements, you're sort of emergently learning a lot of the properties of the system that you otherwise maybe don't know. And so that's just something that I think is like really cool. But you can't do that kind of latency-aware load balancing without being aware of latency, and you can't be aware of latency without being aware of the application layer protocol. Another thing is that HTTP2, right, is, I don't know how much are you all familiar with HTTP2 and what makes it different from HTTP1? Okay. So sort of the main thing about HTTP2 is that HTTP2 is a streaming protocol. And what happens with HTTP1 is that you just send individual requests and then you get back a response, and maybe there's like a transfer encoding chunked or something, so that response might come in a few pieces and you can use that to sort of do long polling, and that's like kind of like a streaming protocol, but that connection is still having one request in flight, one request comes back, so you do this maybe complicated connection pooling where you make a bunch of TCP connections to the same host and you sort of round robin load balance over them. And, you know, this is a lot of extra effort that you can do, but it sort of works. HTTP2 was designed so that you wouldn't have to do that. HTTP2 was designed so that you would have one persistent connection, and you would load balance, and instead of like load balancing over a pool of connections, you would just have this one persistent connection, and you could send multiple request streams, multiple response streams on the same persistent connection, and you could do that concurrently. So with HTTP2, that means that you really don't have to have as many of these connections, but if you're using sort of a naive HTTP client implementation, you might not know that you want to persist these connections. You might still create and destroy connections for every request. And then for RPC protocols on top of HTTP2, specifically, I'm thinking about gRPC. And gRPC is an RPC protocol that it was originally developed by Google. We're told that the G no longer stands for Google RPC because now it's open source and anyone can use it. But, oh, thanks, y'all. I see that people are saying that it's, so like my brain just operates in a very, you know, breadth first and depth first search. My brain operates in a very depth first fashion, right? So I'm not going to sort of summarize all of these things, and you know, maybe people don't know what I'm glossing over. I'm like, just when I'm talking about stuff, I like to sort of go all the way and then pop all the way back up, and that I guess that's what we're doing, and I'm glad that a lot of people are enjoying that. So where were we? Okay, so gRPC, is it good RPC? It's better than SOAP, right? Some of you probably understood that joke. But so gRPC is it does not stand for Google, it stands for G. It stood for Google once, but all mentions of it standing for Google have been scrubbed from the gRPC website and documentation. I think this is very good. Let's go look at it. Let's look at the gRPC website. I'm going to open Firefox here. This is not at all related, but we're gonna do it. grpc.io. See, find their FAQ. It doesn't say Google on here. Wow, it doesn't even say Google uses it. It's a CNCF project. Okay. Who's using gRPC? A bunch of non-Google companies. It was initially created by Google. I definitely remember the G stood for Google at one point, but there was like a concerted scrubbing of, oh, FAQ. I think there's an FAQ. What does gRPC stand for? All right, you all see this? That's the opposite of plus. gRPC stands for gRPC Remote Procedure Calls. gRPC stands for gRPC Remote Procedure Calls. It does not stand for Google. It stood for Google once, but it doesn't anymore. Sorry, that was a digression. I just thought that was fun. So gRPC is this RPC protocol, and you are sending a protobuf so that you have this sort of binary encoding that's like structured data, and you're sending these protobuf messages, and the transport layer for that protocol is HTTP2. This actually gets me into a whole long sort of spiel about the OSI like 7-layer networking model that we could go into, but that's a whole other stream. So you're sending these protobuf messages over gRPC, and gRPC is designed so that these messages can be sort of multiplexed over one HTTP2 stream, and all of this sort of falls down with kube-proxy load balancing. We are finally going back to the question about how is this different from kube-proxy that another Walter asked, I promise. So kube-proxy is a round-robin load balancer. It picks the next IP, picks the next IP, picks the next IP. And it does this every time it gets a TCP connection, right? So whenever you create a new TCP connection, kube-proxy picks the next IP for you. And what that means is that when you're using gRPC, where you might send a whole lot of requests over one connection, you create that persistent connection. Kube-proxy goes, oh, okay, this is to that service. I'm going to pick, you know, the IP address 555.555.5. That's not a real IP address because, you know, they can't have 5 in the third digits place because it's a byte. So you know, don't try to dial this TCP address or this IP address because no one's there listening because you can't. Right? Okay. So I totally forgot where I was going with this. So Linkerd-proxy just picks some endpoint. It sends that connection to that endpoint, that TCP connection, and then that persistent connection in HTTP2 has a whole bunch of requests going on it, a whole bunch of responses coming back. You are now talking exclusively to that one endpoint. You know, if you are obeying, you know, the gRPC protocol, and you are just sending more traffic on that persistent connection, everything is just going to one place. Can you? Yes. That's actually another great question from another Walter. People have done this. There are definitely some blog posts about people auto-scaling on Linkerd latency reports, because these latencies are used for load balancing, but they're also part of Linkerd's observability features, right? So we have a bunch of Prometheus metrics that we expose, like here's request latencies, here's response times, here's all of these like latency histograms, and we break it down by every like service and every, you know, all of this like really detailed metrics that we can just generate because we're in the data stream on the wire, we're in the data plane, all the traffic is going through us. And it turns out you know a lot about how an application is running with no actual knowledge of what it does if you're just sitting there on the wire and all of the traffic is going through you. And you can definitely do latency-aware autoscaling, and it's actually a great metric to autoscale on. I know that there are some blog posts and some demos of autoscaling with Linkerd metrics. I don't have them, you know, right here in front of me, but I'm sure that you could find them, or somebody else in the chat could just probably Google Linkerd autoscaling or something. You'll find something good. So yeah, you absolutely can do that. But again, if we want to talk about latency, we have to know about higher level protocol concepts. And we can't talk about latency when all we see is an opaque byte stream. We have a metric in Linkerd of what's the duration of TCP connections. That metric isn't very useful because they just sort of last for a really long time. It's not telling you how slow or fast requests are being processed. It's just telling you, you know, maybe those endpoints stick around for a really long time because you're not like rolling them because you don't need to roll them. So it's just not a super useful metric. But because we're aware of the actual request and response traffic, just popping back up the stack to the load balancing question, because we're aware of the actual request messages and response messages and not just aware of the TCP connections, we can have one persistent connection from the application to the proxy. All of these requests come in on that persistent connection. We pick them and we go, oh, you know, this is a new request. I'm going to send it to a new replica. And we have a persistent stream to that replica already, right? Because we're already talking to them. And we have a persistent stream to maybe 10, 20, 100 replicas, and we load balance over those persistent streams that we've already set up. Linkerd-proxy can't do that. And, you know, in some ways, like, Linkerd-proxy shouldn't do that because Linkerd-proxy isn't intended to do that. This is not like, oh, Linkerd-proxy is bad software, or even like your ELBs are bad software. It's just, that's not their intended use case. They're not supposed to be application layer protocol aware because they are just trying to load balance at the lowest possible common denominator, which is I have some TCP streams, right? But that's something that an application layer aware proxy can do. We can also do, you know, retries, right? You can't do retries if all you have is TCP streams, because you would just have to maybe copy all of those bytes into a giant buffer, and then maybe that TCP connection never ends and you run out of memory, right? And maybe that connection ends with a connection refused error. Well, how do you know what that means? Like, the TCP errors just sort of mean the connection stopped, right? Like, they don't really tell you, oh, you know, this is a 500 error because there was an internal server error, or like there was too much load on this replica, whatever. They just mean that connection went away. So maybe you try to open that connection again, that thing is gone. Maybe that that endpoint just went away. And you know, like, there's really no difference between closing a TCP stream successfully and closing it with an error. Those are the same thing. There's no real concept of, like, something actually went wrong that caused me to hang up versus just I'm done, so I hung up. So how do you determine if you need to retry? You can't. You don't have that information. But if you speak HTTP, you send a request and you get a response back, and the response is like, you know, 503 service unavailable. Yeah, you can retry that. Service unavailable. That means maybe too much load on this replica. I'll send it somewhere else. So that's something you can do when you're speaking the application layer protocol. You also know, like, what requests are retryable and what requests are not retryable. There are a lot of, like, real horror stories where, you know, I have some REST application or something, and I have an endpoint that's like delete or like create or whatever, and I have something that I want to create one time, and I click like, okay, create thing in the front end, and it sends some REST like /create/ whatever, and it creates a whatever, and maybe that request fails, and so I retry it. Well, maybe I've, you know, created 2 whatevers, or a whole lot of whatevers if I get into some loop where I keep retrying that request. So that's not really safe to retry. But some HTTP methods, like get, is safe to retry. You try to get a resource, you can't get it, you can try it again. Maybe you'll get it that time. So if you want to do these retries, you have to be, it's a protocol layer concept. You can't do it if you're not aware of the protocol. And that was sort of a very long-winded explanation of what's the difference between a Linkerd-proxy and its load balancing and an AWS ELB or kube-proxy or other connection level load balancing. That's also the same kind of load balancing that, like, all of your like F5 like load balancing appliances that come in like a big box that say F5 on them. You know, I'm gonna tell you all a little secret here. Those are not like ASICs, right? Those are just like white label Linux servers that are running like Nginx or something on them. That's all it is. It's just Nginx. It's just not doing most of the stuff that Nginx could do. I mean, I don't know if they're Nginx specifically, but it's something like that. Those are just like, don't buy hardware load balancers. They're not hardware. I mean, they're software load balancers, right? It's just that they come with hardware. Don't buy them. You know, there's no reason to buy them. If there was like an application-specific integrated service that was a circuit, right, like an ASIC that was able to like load balance over TCP connections, yeah, maybe buy that. But like, these aren't that. They don't do that. They're Linux servers. They're just bad Linux servers. They can only do one thing badly. Don't buy them. But they also are doing that layer of load balancing, is the point. If you think that an AWS ELB is a hardware load balancer, that's also not true. But where was I going with this? We were going to look at Linkerd-proxy. Right. We were going to learn about proxies, which I guess we are doing anyway. So we have this app module, right? And this is a crate, and it has a bunch of crates in it. And remember how I said that we have an inbound direction and an outbound direction, right? So we have traffic that is going into the container from, you know, who knows where, the entire rest of the world. And then we have traffic that is leaving the container, going somewhere else. So we have an inbound and an outbound here. And this is where it sort of starts to get interesting. So we have this outbound, we have a lib.rs, that's sort of the main module. We have a bunch of imports here, ignore that. Turns out that we import a bunch of stuff. And then we have this, let's find, where do I want to go? Build HTTP router. Right, so this is a function that builds an HTTP router. So this is going to take a bunch of stuff and then it's going to give us back something. We'll learn about that later. But we build a load balancer here. And this is where we sort of have this abstraction that I think is very cool. So we say, like, all right, we have this HTTP load balancer, and we start out, we make this stack thing, learn about that, and it starts out with an HTTP endpoint, and then on top of that HTTP endpoint, we have, we sort of push all of this stuff. And we push a metrics layer, and then we push a cache that's caching endpoints. I actually picked a bad place to start looking here, because there's sort of a lot going on. Let's look at inbound instead, and let's look at here, build server. So here's where we're building a server, and in this server, we have, okay, this is a request, HTTP request as they're initially received by the proxy. So we have some layers, and then we're going to combine these layers in some kind of a way. And so we start out, we say, okay, we have this layer that's an original protocol downgrade layer. And what that means is that maybe we have something coming in on an HTTP2 connection, and we have some header that says, this was originally an HTTP1 request. So maybe the application that sent this request thinks that it's speaking HTTP1. Maybe it doesn't know about HTTP2 at all. Maybe if the request was sent in HTTP1, the application thinks that it's speaking HTTP1. Maybe the endpoint that it's trying to talk to also speaks HTTP1. We don't know that. So we have this header, and if we see this header, we know, okay, this was sent as HTTP1, so we have to downgrade it back to HTTP1, regardless of what we did on the wire. And that's, as a side note, kind of the really cool thing about the service mesh model of having these separate sidecar proxies next to every application instance, instead of having one big proxy that everyone sends all of their traffic to, and then it fans out from there. You have two proxies, and then two proxies are talking to each other. And having two proxies means that there's 4 network hops now. Maybe that's, maybe having 4 network hops is sort of a double-edged sword. It can be used for both good and evil, right? Like, a lot of people are like, oh no, there's, too many network hops. That's bad, because now we have more TCP connections, and it's going through there and then going through there, and that makes it slower. Maybe. But on the other hand, there's all kinds of really magical stuff you can do when you have control over both ends, right? Like, all of the time that the request spends on the wire, it is going from one Linkerd-proxy to another Linkerd-proxy. There's 2 hops. There's a hop on either end, right? From application to proxy, proxy to proxy, proxy to application. But the proxy and application hops, that's on localhost, right? We know that these proxies are co-located with the application container. So they're just talking to each other on a loopback interface. And that's really good, because that means a bunch of things. Loopback is pretty fast. The overhead of talking to someone on localhost is the overhead of, you basically do a syscall, right? Like, there's a jump into kernel space to write those bytes, and then there's a jump into kernel space in the recipient to receive those bytes. But the socket is really just a buffer in the Linux kernel somewhere. It's not going on a wire and doing like all of this stuff. All kinds of bad stuff happens on wires that doesn't happen in ECC memory in your fancy enterprise server. You have these, like, TCP is very complex. You have these sequence numbers and all of this stuff. And all of this stuff is so that, like, sometimes a packet just goes away. You never know. Like, the internet, it turns out, is sort of bad. And, like, these wires just sometimes don't work. And they're, like, collision domains and all of this, like, stuff that happens at, like, really low levels of this OSI model that, you really just don't care about at all. And, like, way down there someplace, there's this, like, level of voltages and wires and frequencies, and how are these bytes actually being encoded in sync words and all of this like crap. And you don't care about any of this stuff, and it's all pure overhead. But we need it because this is how two computers talk to each other. So if that request is going on the wire, you're paying the cost of like all of this stuff, modulating and demodulating and voltages and sync words. You're not paying that cost when your TCP connection is really just going over like a ring buffer in the Linux kernel or whatever. You just write some memory and then you read from some memory, and like that's basically, like you have these syscalls. Syscalls aren't free, but it's like an order of magnitude difference between, you know, the electrical engineering stuff and the like, it's just like some RAM in the Linux kernel. And in these servers, the RAM is ECC RAM, so it's not like those bits ever get flipped. So it's not like these like TCP packets are ever sent out of order when you're just writing them on localhost, right? So all of this like complicated stuff that TCP does to sort of reassemble like the higher level protocol data, you don't need to do that when you're just talking on localhost. So all of this sort of, there's a lot less overhead for the loopback hops than there are for the like actually going on a wire hop. And the actually going on a wire hop is where all of the interesting things happen. Okay, Alex. So the actually going on a wire hop is where all of the interesting things happen. It's where all of the latency lives because, you know, you go top of rack switch, end of rack switch, and so on and so forth. And that's where like 90% of the time is spent. On the wire is where, hi Katie, on the wire is where the bad guys live too. Right, like if your wires get tapped, you know, it's when the traffic goes on the wire that it gets stolen, and so on and so forth. Right. So if we want to make our traffic fast, we care about what's happening when it is traveling between computers. If we want to make our traffic secure, the primary thing that we care about is what's happening when it's traveling between hosts. I mean, we care about what happens on the host too, but that is sort of another unsolved problem in computers. So that hop in between the two proxies is the important one. And in this sort of model where you control both ends of that hop, you can do all kinds of stuff, right? Like if you have one big proxy and you send traffic to that big proxy, and then it sends that traffic out into the world, both of those hops are basically going to have to speak the same protocol, right? Like, it has to be HTTP1, has to be HTTP1, because if the proxy wasn't there, you would just be speaking HTTP1. So both hops on the wire, you are using HTTP1, so one request per connection. When you have two proxies, and the two proxies are located right next to the application, there's no guarantee that the proxies are speaking the same protocol as the applications. And that's really kind of magical, because HTTP2 has these sort of better connection multiplexing properties. It's designed to sort of work around the fact that like an HTTP1 request kind of ties up a single TCP connection forever. Right, and that like then we have to make more connections. There's more file descriptors. It's more, you know, there's a big array in the Linux kernel of all of the file descriptors and so on. And that's all just like a bunch of crap that we don't care about. We just want to send a bunch of requests to the same place. So you can do that, and you can do that by sitting on both sides of the actual physical wire and turning all of the traffic on the wire that's over multiple connections into a bunch of multiplex requests on a single connection, and then you just have to tell the recipient, hey, I did all of this stuff, the application doesn't want to know about it, so make sure that you don't tell the application that we did all of this stuff that just happens to magically make everything faster and more reliable. And it's the same with encryption. You know, you have this maybe, like we talked about the perimeter security model, and we talked about this sort of, you have a big ingress load balancer, big ingress nginx or something, and it terminates TLS for like my.website.com or whatever, and you have one big cert that's signed by Komodo or whatever, and just says like, I can terminate TLS for, you know, my.website.com, and I can do this because Komodo says I can, and why do we care what Komodo says? Because they paid someone a lot of money to gain the power to do that. And so you just have this sort of model where once the connection comes in from like my web browser to your data center, and it hits that big ingress proxy, and it goes, oh, this is, you know, some TLS traffic. I have this cert that says like I'm my.website.com, so I terminate TLS. Now you're just passing around a bunch of bytes that are like totally decrypted plain text that anyone can read, and that's not super great. And it's one thing if all of this hardware belongs to you and it all lives like, you know, under your desk, right? Like maybe you can trust that. But when all of this hardware belongs to like a public cloud and it's not even your hardware exclusively, because maybe there's somebody else's VMs running on the same hardware, and maybe there's even somebody else's container running in the VM, and also you are a massive company and you don't really trust the guys in the room next door, you have this totally different world where you can't trust that perimeter. You can't say that this is the trust boundary. Everything within this perimeter, totally safe, and we're just going to, you know, talk plain text everywhere, and it's totally safe, and it's fine, because that big perimeter of like we have one ingress router and it terminates TLS for everyone is not really sufficient to protect you in a world where you don't own the hardware, and you don't even have exclusivity to the hardware that you're renting. So instead, you need this sort of zero trust model where you don't say, oh, we have this perimeter, and within that perimeter everything's safe. We assume that the network is hostile, and if we want to talk to someone else, no matter who it is, and even if we're best friends with them, we have to make sure that they're not somebody else pretending to be them, and we have to make sure that nobody else is listening, even if we're like in our, you know, home. And this is kind of a fucked up world. It's pretty grim when you think about it. Like zero trust actually means that you can't trust anyone. It's kind of messed up. But it's the world that we live in, and if we want to have our applications be reliable and we want to be able to, you know, not have these big data leaks, or, you know, if we want to respect the privacy of the people who are actually using the application, we really need to embrace this world where everyone is constantly trying to kill you and has knives behind their back all the time. And if we live in that world, we need to encrypt all traffic, even when it's within that perimeter. And this is a hard thing to convince people to do, especially when they have code that already works, right? Because in order for it to work, it has to be done pretty consistently. And so you don't really want to go like, I have a bunch of microservices, I don't really want to go around and talk to every like individual developer who is running one of those like microservice teams and saying like, you want to build features for the application because that's what you want to do because you're an application person, and you have to go to all of them and you sort of say like, you know, I know that you like want to build features, maybe you even want to fix bugs if you're like particularly virtuous, but you know, I need you to stop doing that for a few minutes and I need you to figure out TLS. And then they say, well, I thought we had that like one big ingress engine X with like a cert that's signed by Komodo that says that we represent my.website.com. Doesn't that mean we're already doing TLS? And then you have to say to them, it does mean that we're already doing TLS, but then, you know, inside of our like AWS thing that we're paying for, we're not doing TLS anymore. What the hell? You know? Like, and so you have to go around and tell all of those people, now you have to care about this thing. And then they're like, well, I'm not a cryptographer, and like, I don't know about TLS. And then you have to say to them, well, you know, you have to do it. And then they're like, okay, do we use like OpenSSL or boring SSL or, you know, it's a whole big thing. And then you have to distribute key material to all of those separate microservices teams, and you have to like teach them how to respect key material and not leak it and not let it leave a host boundary, not store it on disk. It's a big ask. It's a lot to say, okay, we now live in this world where everyone has constantly got it out for us, and now it's your responsibility. And if you want it to be consistent, it's like maybe somebody has an SSL library that only uses like TLS 1.2 and somebody else can speak TLS v3, and there's like all of these incompatibilities and everything is constantly broken. And like, it's a really big ask to take an application that already works and totally break it because you heard that there was a data breach at some other company, and now we care about this. But when you control both hops, right, when you control all of the hops on the wire, and you have the same proxy on both sides, you can consistently roll out mutual auth everywhere. You don't have to worry about solving this problem of how do I get like every application service team to, you know, have a working TLS story and like have a PKI and all of this stuff that they don't know or care about. You just flip the switch. You say, okay, I want Linkerd to do TLS. And since the other hop is on localhost, right, you are much less vulnerable because that traffic just goes into the Linux kernel, stays in the Linux kernel, and then it comes back out into the proxy. And you know, there's like Spectre and Meltdown, and those are bad. And like, so there are still, you know, some potential vulnerabilities when the data is just in the only plain text in the kernel's memory. But you know, we are working on fixing those, right? Like there are mitigations for Spectre and Meltdown that sort of work. And I'm sure that like Intel is going to have like another like branch prediction mistake in the next like 6 months because I feel like we're overdue, and they just leaked all of that like Intel technical stuff, and so I'm sure somebody's going to find a cool branch prediction mistake in there. But you know, you can have it's defense in depth. You can have a much more like reasonable level of security without having to deal with like OpenSSL and boring SSL and like other non-boring SSL implementations, right? And they're still called SSL, even though we call it TLS now, because they were written in like however many years ago when we still called it SSL, and right, that's not great. So when you control both of those hops, you can do all kinds of things. And I guess we got into this because we saw this protocol downgrade, and I was sort of like, okay, we see this downgrade word. Downgrade seems bad. Well, sometimes it's actually good to downgrade, and that's the story of why. And then, you know, we take this, we have this request coming into the proxy, so we create this admit request layer, and then we have an observability layer, and it looks like it does some tracing stuff, so that's doing like some open census distributed tracing propagation, and we have this HTTP server. And so we say we take an HTTP router, and we push a timeout onto it. So we're saying when we're routing these requests, we want to add a timeout to how long it takes to obtain a ready service for that request. And then we have a router layer, and we have a layer here that strips HTTP headers, and we have a layer here that is this admit request that we looked at up here, and we have this HTTP server observability layer that we looked at up here. And so we're just sort of composing all of this stuff together to build one piece of functionality. And the cool thing about this is that this model is based on composition, oh, hi, sorry. So this is my first ever stream. I have no idea what I'm doing, and I'm trying it for the first time. And we're taking a little tour of the Linkerd-proxy, and sort of at a very high level. And so we have this sort of model where all of these things are being built compositionally. And the cool thing about building things compositionally is that you can plug them together however you want. I recently found a bug in a Linkerd-proxy that was sort of really like ruining my life for a couple weeks. There was this like weird deadlock where we would have this proxy and a load test, and all of this traffic would be going through it, and if it's going in a certain direction, it would serve like 2,000 or 3,000 requests, and then it would just stop. It would die, and nothing would happen. And this was like, you know, there was this concurrency deadlock, like all of this like really hairy stuff, and it was just kicking my ass, you know? It was like a week from hell. I would just like keep adding like debugging and like turning stuff off and like messing with parameters and just trying to figure out what was happening. I was like poring over logs and I couldn't figure it out. It was impossible to follow. But what I was able to do is I just took all of these stacks that we have here where we're, shut up, Manish, don't. Oh my God. there is a crate that helps you out with logs. And I was using those logs. And they were like very nice, structured, like easy to read. Like I still couldn't figure out what was happening, because what was happening was that eventually it would just stop. No, I know. So what I would do is, the way that I solved this problem, I just commented out everything in between, like the very top and the very bottom of these stacks. I ran the load test, and it worked. Okay, cool, it's somewhere in between here and there. And then I went back in and I sort of, line by line, just each of these layers that were composing together, which I had just commented out, I started to comment them back in, or uncommented them, I guess. I brought them back, one layer at a time. It took me like 4 tries, and I was just sort of bisecting. You don't get bisect, right? Like you take a bunch of commits temporally, right? Different points in time, and you try to find a bug by like picking a commit that works, picking a commit that doesn't work, and then sort of testing each pair like that until you find a place where if I'm on this commit it works, if I'm on that commit it doesn't work. Well, you can do that not temporally but semantically here, right? You can bisect the code. You can bisect the actual behavior of the program at a point in time. And by doing that, I was able to find a bug in like, I think it took me half an hour. It was a deadlock. It was in code that I wrote that I was like very proud of when I wrote it. And I was like, this is very cool, like an awesome code that I wrote. And I was like, this is awesome. You know, that's where the bug was. But I wasn't able to find it because, you know, just looking at the logs, it turns out the reason I wasn't able to find it just looking at the logs is the cool code that I wrote that was like very like awesome and like advanced and I was very proud of didn't have any logs in it. You know, because I thought that it would never break. But this sort of compositional model was very useful because we could sort of just tear the application apart and then put it back together bit by bit. And this doesn't work as well when you are building it based on like everything knows what the thing that is in front of it is and the thing that's behind of it is, right? Like if you have this sort of object-oriented model where you have classes and each class you have like a proxy class, and the proxy class owns a router class, and the router class owns a connection class. It's hard to take out like one thing in that sort of hierarchy of things owning specific other things. It's hard to move things around because, oh no, now the router class doesn't own the connection class. It owns the load balancer class, and the load balancer class owns the connection class. Well, you know what do you do? Like you have this diff, right, where like if you want to add something, you touch every file, right? Like you have to go through and sort of like unplug all of the things and then put the new thing in and then plug all of the things back together, and the sort of plugging and unplugging means that you end up changing everything all the time. But with this sort of model of composition, we don't really have that. We have this like one file, right? We're looking at this inbound live.rs, and this live.rs is a map of the entire inbound side of the proxy. And this is where we plug all of the things together. And because we plug all of the things together in that way, I could just like copy half of this and paste it somewhere else, and it would still work. I mean, it might not do what it's supposed to do, right? Because now I've made the proxy backwards or whatever, but like, we can just move this functionality, and we don't have to touch any of the implementations of that functionality. That functionality lives in some crate, right? One of these like many sort of sub-packages here that are called like, you know, buffer and cache and drain and DNS and error metrics and HTTP classify and HTTP metrics and so on. Those implementations are totally self-contained, and they don't have to know about, you know, after the HTTP metrics we put the cache, and after the cache we put the DNS resolver and then the load balancer, because they don't own like the next thing, or the next thing doesn't, or the previous thing doesn't own it. Instead, we just sort of have this model where we define these interfaces, we say, I know how to do that, and then we can plug them all together, and we end up plugging them all together in one place, and we have sort of this nice map of the whole thing, and we can move something or get rid of something or add something just by changing the map. without touching the implementations. And that's kind of magical to me. And in a minute, I would like to take a quick look at sort of the fundamental abstractions that let us do that. But I'm going to take a little break to get some water, and I'm going to switch to the please wait. And I will be right back with you after the break. I realized just now that I didn't turn on audio when I'm showing this screen. Okay, folks, I am back, and we're going to pick up where we left off, which is someplace that I no longer remember where it was. Where were we? We were talking about abstractions, and we were talking about the way that we build this proxy by sort of composing all of these pieces together. And particularly, there are a couple of very fundamental abstractions that are sort of critical to this whole sort of architecture, this whole sort of design that we have here, really relies on a couple of things. And the first thing that Linkerd relies on is we rely on the future trait. How many of you in the chat, or how many of you watching the stream, have used futures? Or in JavaScript, they call them promises. In Scala, they call them futures. I think Java has futures now. A bunch of languages have some concept of a future type. And what does that represent? A future represents some value that might be here now, or might be there in the future, right? And a future gives us a model for doing asynchronous computation. And asynchrony is sort of, honestly, it's table stakes, right? It's table stakes for if you want to have a network application and you want to have like a very high amount of concurrent traffic. It's kind of table stakes. You kind of need some form of asynchronous I/O if you're going to play this game. You need to have some kind of event loop, and you need to not be handling all of the input and output that you're doing, because you're handling thousands of concurrent connections, and you have all of this, you're very I/O bound, and you spend all of your time waiting. And if you spend all of your time waiting in an application that's just okay, I'm going to spawn a new thread, and every time a request comes in, I'm going to spawn a new thread to handle that request. You know, the secret to that is that is actually fine in your Rails app. It's actually fine to use threads in your web application, in the actual backend application, because the overhead of actually doing application stuff is orders of magnitude greater than the overhead of, scheduling a thread, and the kernel has to make a thread, and it has to wake up a thread, and then your thread has to block, and all of the stuff that happens. Okay, yeah, that costs a lot. But it costs a lot more to do work, right? That people actually want. That costs a lot more. Linkerd doesn't do work. I mean, it does work. It does, it forwards traffics, right? But it's not doing any application. It's not providing a useful thing to a client. It's providing benefits to the application and to the application developers. And all it's doing is forwarding traffic, right? The I/O is the point. It's not a compute-bound system. It's not something that receives a request, and when it gets that request, it's I'm going to add a billion floating point numbers, because somehow this is useful to some kind of person for some kind of reason, right? I'm going to process an image, and as soon as you process an image, it doesn't matter how many threads you spawn, because you're sitting on the CPU forever, and the request's latency is now coming from actually doing the job that the computer's supposed to do. And that's good and beautiful, because that's what makes computers useful. And otherwise, if they could just handle if a computer was just a machine for forwarding HTTP connections and requests and responses and all of this stuff, we wouldn't really want to do any of this, because it wouldn't be doing anything. But in this case, all the work that we're doing is receiving these requests, receiving responses, routing them, sending them different places. So the overhead of performing that I/O is a much bigger percentage of the flame graph that you get when you run perf record and you have a Linkerd and it's under load, than perf record on your like application service that is like adding a bunch of floats or whatever. So for us, it's very important that we're not just like spawning a big pile of threads and like waiting for the kernel to wake all of them up and like waiting for kernel scheduling overhead all of the time. And if we're going to handle thousands of requests per second, we need some kind of, as efficiently as possible, right? Because this thing is deployed side by side with every application instance. That means that we're not running on, you know, a big, like, AMD EPYC server with 64 cores. I mean, we are, but we don't get to use all 64 of those cores, right? Because if we use all 64 of those cores and we use them just for sending traffic around, that's great, but that backend service that actually does like all of the floating point division or whatever it is that people actually want from computers, I don't know, I'm imagining it's floating point. I don't actually know what people use computers for, but it's probably floating point because they put floating point units in like every computer now, and it's like, what do you do with that? I don't know. You can't do anything interesting because you can't do like bit math with it, so it's like, what's it for? I don't know, probably the stuff that people actually want to use computers for. Where did I... Okay. Right. So if you have like this, you know, 64 core like EPYC server with like all of these like, you know, you can have a million threads on this thing, whatever. That's like all very great. Linkerd can't have all of those threads because the, you know, the floating point summing thing is actually using some of that. And if we spawn a thread for every connection, we saturate the NIC, we saturate, you know, it's great that we saturate the NIC. If we saturate the CPU, the request latency is going to go down really fast, even though, you know, we have all of these threads doing forwarding, we're doing all of this like networking work, and we have all these resources for it, but you're not going to get your summed float array back very fast because the thing that actually sums the float arrays is just waiting to get scheduled when we're doing all of this like networking stuff. And then people get mad and they're like, you know, like I'm the floating point summing guy, and I'm like, wait, why is the like network proxy that you added that was supposed to be a transparent layer that I don't have to know about, why is it now like starving my app so that I can't like do that? You know, so it's very important for us to not just be fast because we're adding all of this latency in the request path, but also to be efficient because, you know, every CPU second that we use is a CPU second that the application is not using, right? So we want to give these value adds that we talked about that are like super valuable things to be able to do, like the load balancing and stuff. That stuff is only worth doing if the trade-off of, you know, in return for getting like load balancing that makes your app faster, you have to like spend time doing that load balancing, right? So if the proxy has to be fast, it has to not add latency in that request path. But more importantly, it has to do that as efficiently as possible. And if we're spawning a whole bunch of threads, you know, for like every connection, every request, we're not efficient anymore. Maybe we are able to handle thousands of RPS because we're running on a 64 core like dual CPU EPYC board on a blade server with like a whatever. Maybe we're able to handle all of that traffic, but we're handling that traffic at the cost of like occasionally an application thread gets scheduled. So by handling those requests asynchronously and using non-blocking I/O, we are able to get a lot more done with a lot less CPU time, right? And because of that, asynchrony is really important to us. There was a really good comment from someone on the internet that I think about a lot, that I think is very useful. And it's sort of, you know, the expression that concurrency is not parallelism, right? And that's true. Concurrency is not parallelism. But asynchrony is not concurrency or parallelism, right? These things are related, but they're also not the same. And the comment that I saw that I think about a lot was the comment that threads are for working in parallel and async is for waiting in parallel. And I think that's very good because, or it's very apt, because if you write this application and you have to sum all of these floats, you just take like half of the floats and you give them to one thread and you say, hey thread, go sum all of those floats, and you take half of the floats and you give them to another thread and you say, hey thread, go sum all of those floats. You get your floats back in half the time, and that's like very good. And so you did the work, the compute bound work, in parallel. Threads are very good for compute bound work. For IO bound work, which is what we are doing, right? Because we are a proxy, we are purely IO. The ideal proxy is just a syscall that reads some bytes from a socket and another syscall that writes some bytes to a socket in a loop. Please, somebody write the proxy that's just a loop that's like a read call, a mem copy, and a write call, because that's really all it is. Everything else is just value. It's just actual behavior that you want a computer to do. But for us, we don't need to do work in parallel as much as we need to wait in parallel. We need to, we have all of these connections and we're waiting for more bytes to come in on any of them. And if bytes come in on any of those connections, then we want to send them to one place or a different place or a third place. And we could spawn a thread for each of those connections. But like the network is, how many times slower is the network than anything that happens inside a CPU? It's a big number, right? There's like a power of 10 with some zeros in it. And so you have all of these threads and they're waiting for some blocking IO actions to happen. They're not really getting anything done. But if those threads are non-blocking, what happens is that you have some user space task abstraction. And we call it a task because Rust calls it a task. The Go people call them Go routines, right? Like you could call them green threads, whatever. And like all of those things maybe refer to like a different shape for the task abstraction, but fundamentally it's the same thing. And it's the same thing as a thread. It's just that the kernel isn't the one that schedules the thread anymore. And the thing about that is that you are not scheduling tasks in terms of like being on and off the CPU. Like you're not saying if the task is on the CPU or it's off the CPU. You're saying the task is on a thread or off a thread, right? Like you are treating the threads as though they are themselves CPUs and you are reinventing the kernel scheduling algorithm at a higher layer. And so you are spending all of your time on the CPU either like actually doing something. If you are waiting for some IO to happen, then you just start doing something else. And you sit there and you are always doing something when you are scheduled. And when you are not scheduled, then you're doing nothing. But like you are not getting scheduled and then saying, okay, time to block again, and then instantly getting unscheduled and letting the kernel wake you up. Instead, you are just dispatching these IO events to the work that you need to do with that IO like constantly. So you're making the best of the CPU time that you have. I don't know why I went off on that. Right, because we were talking about futures. And we were talking about futures because futures are an abstraction, and they're an abstraction for modeling that kind of non-blocking IO. Really, they're an abstraction for modeling concurrency in general. That is a sort of higher level, more structured abstraction than thinking about something like a thread. It's also a more structured abstraction than something like a Go routine, right? Because what can you do with a thread? You can spawn it. And you say, okay, I want this thread to run. And then if you're very lucky, you can maybe say, let me know when this thread is done. And when those are the two things that you can do, every time you want to do something more complicated, you have to use like, okay, mutex and convar and barriers and like all of this hairy like systems programmer stuff that you'd probably rather not think about. And that's like not great. But when you have a higher level, more composable abstraction for thinking about like what are these units of concurrency, you can write things that are more like, here's a control flow graph or a data flow graph, instead of like, I have to think about these barriers and convars and waking things up and blocking things and so on. And so a future is giving you a way to model with like higher level sort of compositional modeling. Here's how I want to structure the different tasks that I want to do. And so the future abstraction, which we're going to take a look at, is very important to us. And the future abstraction is like one of maybe the two core abstractions in Linkerd. And we need to understand it if we're going to look at the rest of the proxy. And now that abstraction, which we're all very happy about, comes from the Rust standard library, and we're going to take a quick look at it when I can find it here in a minute. Do we import the future trait in here anywhere? We don't. Fascinating. There we go, future. So future represents an asynchronous computation. Future is a value that may not have finished computing yet. This kind of asynchronous value makes it possible for a thread to continue doing useful work while it waits for the value to become available. Wow, that's what I just said, except that's like one paragraph. God, what am I doing? Okay. So, future is a trait. And trait is a piece of Rust syntax that we haven't talked about yet, although it looks like the current stream chat is mostly just like people who know Rust, and like we have like a bunch of Rustaceans in the chat, but for the benefit of anyone who is either not chatting or watching later, Rust has a concept of traits. And a trait is sort of like an interface. If you're used to Java, or sort of like an interface if you're used to Go's traits, or sort of like a Scala trait if you're used to Scala traits, but it's really not quite the same thing because Rust is not a language with inheritance. A trait is more like the Haskell concept of a type class, which probably only a small subset of you have encountered. And if you have heard of this thing before, you know what it is, and if you don't, what I just said doesn't help people. But we can think of it as being like an interface. It defines a behavior. I mean, it is an interface. We can think of it as being, it is an instance of the abstract concept of interfaces. We can think of it as being like, okay, Swift protocols. Okay, that's a more mainstream reference that I haven't thought of because I've like never really looked at any Swift code in my life. But I do happen to know that there's a lot of ideas in common between Swift and Rust, and also I think a lot of like intellectual genealogy in common between Swift and Rust. I think a lot of people who have worked on the Rust compiler were like also hired by Apple to work on Swift, and then some people who worked on Swift have also worked on Rust, and so there are a lot of ideas in common, and apparently Swift has a notion of protocols, and protocol is like a trait. So if you know about this, that hopefully is useful to you, more so than it is to me. But we have these traits, and traits define a behavior that can be implemented by a type, and this trait is called future, and it defines here an associated type. And an associated type is like every implementation of this trait provides a type that is the value of its associated type. I realize that that sounded like nonsense, but a concrete example is better. Here the associated type is called output, and it's, according to this comment, the type of the value produced on completion. Okay, so you have this future that represents a value that may or may not exist yet, and then you have a type, And that's the type of the thing that you will get when the future is complete. So we have this output type, and then we have a method, and that method is called pull. And pull is the only method that this trait defines. And you know that this is a method because it takes a self parameter, right? So it takes this self here, and self is like this. Some languages spell it this. Rust spells it self. Python also. And Rust, here we see like that this self is a thing of type pin self, which we don't care about. Ignore that. It's very important, but for reasons that only matter to you if you are an experienced Rustacean and you were trying to write an implementation of this future trait by hand, all you need to know, for those of you who are new to Rust and new to async in Rust, is that this pin thing is a bunch of nonsense that you don't have to worry about, and it's very, very complicated. So we have this pull method, and we can look at this and we see that it returns something called a pull. And the pull is parameterized over the value of the associated type output. So this pull, we don't know what this pull is yet. I see that there's a large pile of documentation here that I'm not going to read because I never read the documentation. So we can just throw out that giant comment. You see how it's like a grayed out sort of color that's like not as bright as the actual code. Yeah, that's because nobody reads that nonsense. Just ignore that. It's great because it's less important. Instead, we just look at this thing. What is a pull? So this is one of those enum types, right? This is like the result that we were looking at probably about an hour ago before I got sidetracked talking about like NICs and data centers and wires and fiber optics and electrical engineering and all of that. So before I was talking about all of that nonsense, we were looking at the Rust result type, and we were looking at how the result type is a value that is one of multiple variants. And so here we see that this pull thing has a single type parameter called t, and it has two variants which are called ready, and ready is a t, and pending is nothing. And here's where we maybe do want to look at the comment, because we see this here that when a function returns pending, the function must also ensure that the current task is scheduled to be awoken when progress can be made. What does that mean? Well, we don't know. We know that it means that when we return this thing called pending, that means that we are waiting for something. We are waiting for some I/O to be performed. And instead of like, okay, the thread, the thread blocks, and it blocks by, there's like a yield syscall somewhere that it calls that syscall, and it tells the OS like, okay, I can't do anything else. Or, it blocks by just trying to read some bytes from a socket, and the kernel just decides, okay, well, you can't have those bytes now. You have to sleep. You don't get a choice. But here, we're modeling that with actual data that we're actually operating on at the level of the programs that we write. We have this pending thing, and that pending thing is just a piece of data, but in this case, it represents the same thing as, the OS saying, well, you can't read any more bytes, so you just have to sleep. So we return this thing when we can't do any more work. And then it says here that we have to make sure that we are scheduled to be awoken again. That's the difference between those sort of blocking I/O model of you can't read any more bytes right now, so the OS says it's just time for you to stop, right? Because the OS knows what's good for you, right? Like the kernel is sort of like a nanny state that's like, okay, you can't read any more bytes now. I'm cutting you off. We'll come back to you when I think it's right, and I think that you have more bytes on that socket. But for now, you just have to go over there and wait. Here, in this user space model, we can't do that, because all of this is happening in user space, and we're abstracting over threads that we have spawned that the OS manages. We're not abstracting over cores that we can't touch, that only the OS knows about. So here we are responsible for making sure that we get woken up again. How do we do that? Let's go back and let's take a look. Why is there no back button in this goddamn editor? Is there a way for me to go back to where I was before? Is there a way to go back in Visual Studio Code? Okay, if I had Vim bindings. Well, I don't have Vim bindings because I don't hate myself. Alt left arrow. Oh! Oh, I went to a place. That was interesting. None of this is what I want. Okay, so let's pretend that I know what I'm doing, and we're just going to go to the place where we were before. We were looking at the future trait. Control hyphen. Nope, that just makes the font size smaller. Control underscore, that doesn't do anything. So we're just looking at this. We're looking at this future thing. And we see here that we are returning this poll, and if we are done with what we're doing, we return a poll that is ready, and that ready contains our output. If we are not done with what we're doing, we return a variant of poll that's called pending, and then we're responsible for ensuring that we are scheduled to be woken again. So maybe the way that we do that is we have this other argument. We take something called a context. And this context has a thing called a waker. And the waker is a thing that we can get from the context. That's very useful. And it has one method, and this method is called wake. And I guess we can ignore what's happening in here because this is all very complex, like deep Rust internals that we don't need to know. All we know is that this thing will wake us up. So we're given this thing that we can use to wake ourselves up when we are not able to do anything else. So we have this future trait, and now I think we have all of the parts of it laid out in front of us well enough to sort of understand what it actually means. And this future trait has this one method, poll, and we have a self, and it's mutable, so we get to change the state of self. And then we have this context, and this context has something called a waker, and we can use this waker thing to schedule the task that is currently being polled to be polled again. And then we can return something that is either ready or pending. If it's ready, it has some data. If it is pending, it doesn't. And if it is pending, we somehow ensure that this waker is used to schedule the task again. And the cool thing about this is that this is a very simple abstraction. But it too is compositional. This future abstraction means you can have a future that owns another future. You can implement future for a struct that has another future inside of it. And maybe it has two futures. And when you pull that struct, maybe it picks one of those features or maybe one of those other futures, and it pulls that future, and if that future is ready, it does something, and if it's not ready, it does something else. And you can pass that context, right, that contains the ability to schedule the task to be pulled again, which is really your ability to say, it is now okay for me to go to sleep, right? Because I have this thing that I can indicate what I'm waiting for with, right? So you can pass that context to some lower level thing that you are layered on top of, and you can say, here's my context, you know, wake me up when whatever the thing that I'm waiting for is ready, if it's not ready right now. So that's one of these sort of two core abstractions. And this is how we model all of these asynchronous operations. Now this future trait is a little bit complex, and it's a little bit hard to write these by hand. Partially because of that pin thing, which remember how I said the only thing that we need to know about this is that it's complicated and scary. Is Tokyo a waker? Tokyo is... Oh, I see, you're just trolling me. Okay, I thought this was a serious question. Tokyo and any other reactor abstraction, any other event loop, is going to provide an implementation of the waker trait. And it's going to say, like, waker is a hook that the event loop can use to say, here is how I schedule something that needs to be pulled again. And that's the other very cool thing about this, is that this means that the asynchronous runtime in Rust is just built into a library. And that's very nice. Very nice thing about Rust. Because, you can do asynchronous programming in Go, right? You have Go routines. Go routines are asynchronous tasks. The async runtime in Go is built into the Go runtime, right? There is one Go routine scheduler, and it is a very large and very sort of hairy file of this sort of magical Go code that looks a lot like like vintage C. I've read this file. It's very upsetting. And it does a lot of magical things that you can't do in regular Go programs because it's part of the runtime. But in Rust, the runtime is just a library that you can include. So this means we're much closer to a language like C. And in C, you also can do asynchronous programming in C. How do you do asynchronous programming in C? It doesn't have futures. It doesn't have Go routines. You can't have these sort of like nice higher level concepts. It certainly doesn't have green threads, right? You can do asynchronous programming in C. How do you do it? The answer is very, very difficult. You might use a library like libuv. You might write a loop over equal yourself. But basically what it means is that you have to actually manually, you the programmer, have to interleave all of these things that can happen while you're waiting for another thing to happen, right? Like that sort of fundamental principle of what it is to be asynchronous is that when we're waiting for one thing to happen, we're doing another thing, and you sort of have to write an event loop that sort of interleaves all of these things together. You don't have a runtime, you don't have abstractions. In Rust, we have abstractions, but we don't have a runtime. And I think that's something very beautiful about Rust. This is a sort of side digression, but I think that it's very beautiful about Rust that we do have Rust is not Lisp, it's not Haskell, it has a great deal of syntax. And a lot of the syntax is very magical, and they're it's not, homoiconic, and it's not like there's one piece of syntax that you use to model all of these things and everything else is in a library. It is a big language, it's a complex language, it has a lot of syntax, it has a lot of magical things, but the behavior of those things in many, many places are not baked into the language. The meaning of the syntax, the meaning of, we're going into the async syntax is where I'm going here. The fundamental sort of behavior is baked into the language, but that behavior calls into a hook that can be provided by user space code in one way or another, right? So it's not baked into the language. The language has syntax whose behavior you can plug into. And I think that's a very beautiful and valuable thing about Rust, maybe more valuable than some of the other things that a lot of people like about Rust, like, oh, it's memory safe, that's very good, it doesn't have GC, that's very good, especially if you're doing things like you care about a GC pause, that's very, very good. But the most important thing to me is that we have this sort of language where I can just read the code for stuff and I can take it out and swap in something else and it's and I think that's very beautiful, but also very valuable. And I realize that this is totally off topic. So this future trait is very hard to write on your own. But it turns out that a very nice thing about Rust is that some of you have probably seen that Rust has this iterator trait. And iterator is sort of like future, in that a future mutates itself and it maybe returns ready or not. Well, an iterator is sort of like that. It mutates itself and it has this one method called next, and it either returns something or nothing, and nothing means that you've iterated all of the things. And okay, that's very nice, but this interface is sort of hard to use. If you wanted to use an iterator, you would have to write like next, dot next, dot next, dot next, or maybe you have a loop and you write like while dot next is some. That's not very nice. But you can write these for loops, and the for loop is just syntax sugar for using an iterator. A for is a binding and then some expression that's something that's an iterator, and so you just iterate over that thing, and that's all the for loop is. Async Await in Rust, this is where I'm going here, is very similar to that. It's a little bit harder to write these futures by hand than it is to use them by hand, which is sort of the difference, is that it's easy to write iterators, it's harder to use them. So we have this abstraction, and here the abstraction is async functions, right? So we have this function here called build server, and it has this async keyword in front of it. And what that means is that inside of this function, all of this code, right, don't pay attention to the where clause. That's not what we're here to look at. Where was I? This build server function. Normally when you call a function, you just get something back. All of this code in the function runs immediately, you get something back. What this async keyword means, though, is that we don't get a result back when we call this function. We get back something that is a future. We get, under the hood here, we get a future that has the output of result or of nothing or an error, right? So none of this actually happens. Instead, we get a future that does all of this behavior. And in that future, we can write the await word. Except in, oh, there it is. There's the await word. And so what that means is that all of this code will run until the first time it hits that await point. And this await point is being called on something that is itself a future. And so what that means is that we generate this sort of state machine that will pull that future until it becomes ready, and then run all of the code until it hits the next await point, and then it will call whatever future is being awaited there, and it will pull that future until it becomes ready, and then it will continue, right? And if those futures aren't ready, then this whole future that is being generated is itself not ready, and it propagates up the stack, and then it yields, and another task is executed, and so on. And so we have that abstraction of being able to write these futures, which are this sort of like very low-level interface where you can write futures yourself, but you can also just sort of say, okay, I have some behavior where I want to have this very straight-line code, but some of the things in it are asynchronous, and you can just put those await points in and wait for them there. And that's one of the two sort of fundamental abstractions. And the other abstraction that I wanted to look at is the service trait. And the service trait, okay, so we're in this bullet point now, I suppose. And the service trait is not in Rust, right? It is defined in a third-party library, and that library is called Tower. And Tower is definitely, I would say that it's a library that at least grew up alongside Linkerd. Oliver and myself, Oliver Gould, who is the Cto of Buoyant, we contributed a great deal to Tower. So did Sean MacArthur and Carl Lerka, who at the time worked at Buoyant. We're not the sole developers of Tower. We, Aaron Turon worked on Tower a great deal, and many others, but the Tower ecosystem definitely developed alongside our initial work on implementing Linkerd, and a lot of it was, it's very fundamental to the project. So Tower defines this service trait, and this is actually the biggest trait we've looked at so far. Right, this has like a bunch of stuff on it. Has a generic, so it takes a request. Oh god, what did I do? I clicked someplace that I didn't want to click. We're looking at service. So this is the other sort of fundamental building block that we use to build the proxy. And we have this response, and we have some type that's our response, we have some type that's our error, we have some type that's our request, and we're generic over request, so we might take multiple types of request if we're a service. And then we have some future that we return, and that future implements the future trait. And its output, right, the thing that we get when we await that future, is we get a result that is either our response or our error. And then we have these methods, pullReady, which takes a mutable reference to a self and a context, and it returns a pull of a result, and that is either pending or a result, and the result is either nothing or an error. And that returns ready, okay, when the service is able to process requests. So this is used for propagating back pressure from the service. This is how we sort of say, okay, the service is ready now, or it's not ready and you have to wait. And then we have this call method, and the call method takes a sidetrack thought for this chat. How would one write or create things that can have, do you mean like an abstraction for something on which methods can be chained? Because I think that might be something that you could model in a language with appropriately high-level concepts. You cannot model that in Rust. Back on topic. So we have this call method that takes a self, and it takes a request, and then it returns some future. Process the request and return the response asynchronously. So we have this service trait, and a service is just, basically it's a function. It's basically a function from a request to a response, and there might be an error. And then all of this stuff is just sort of details if we want to do this asynchronously. And what can you do with functions? You can compose functions. You can make a function. I have some function f and some function g. I can use a composition operator, right, to make a new function that is the result of f of some input, of g of some input, right? So I can say like f of g is, I can compose these functions together, and because of that, I can sort of build abstractions out of pieces by sort of composing these functions. And service is basically a function. In fact, it is implemented for functions in many places, not here, but elsewhere in Tower, there's an implementation of a service for a function. And I can compose these things, and I have this layer interface that we were looking at in the proxy that is sort of used for composing these services together. So we can say that a load balancer and a router can be composed together, and we can compose a timeout over a connection in the router, and we can do, and the errors are propagated up the stack, and back pressure is propagated up the stack, and then we can have a service that's composed of many subservices, so you have this sort of tree, and that's sort of the other fundamental abstraction, fundamental proxy building block, of which Linkerd-proxy is built. And we're reaching a point where my throat is actually starting to hurt, so I think I would like to start winding the stream down now. And we've gone over quite a lot, and gosh, it has been a fairly long time. So I did want to set a little aside at the end for a little last Q&A, and then maybe talking about what we're going to do next time, because it seems like folks have had a good time, so I might have to do this again. And so if anyone has any questions about what we looked at today, I'm absolutely happy to answer them. Well, I will definitely do a repeat stream then, if this was fun. I'm glad that people seem to have enjoyed this. Next time, I think we might be digging a little deeper into proxy internals, although I still also think that it might be very fun to do some live coding. So I guess we'll see when we get there. Next time, cats on stream. I could do cats on stream. It's very, very warm today, so I think that the cats have just found a warm place to sleep. Of course there can be cats on stream. I'm actually sitting here right next to my desktop, where I have all of the heat vents for the big radiator on top, so the cats like to. Okay, subscribe, click the bell, thanks. Thanks to everyone who enjoyed the stream. Don't forget to smash that MF like button. I'm gonna wrap up now. I thank you all for tuning in, and hopefully we'll do another one next week, maybe same time, about the same place. Hopefully the same place. I mean, you don't have to be in the same place, because I'm here. That's not the point. Yeah. Don't forget to like and subscribe. I'm supposed to say that, right?